Okay, so it is time to figure out how to make mechanisms move. So what we've got here is, I'll actually pull up their previous version. This is our elevator from the 2022 robot. And what we have is a cascading elevator. So the idea is you have this square tubing and you have these constant force springs. And so the top, this constant force spring is actually attached to that hole right there. And the idea is that that pulls up. So you these all pull up. At the very top, there's actually a string attached. The string goes all the way down to the bottom, and you have a pulley. So the idea is that when this motor runs, it winds up the string, and that causes these pieces to get pulled down. And when the motor is released, the springs will actually pull it up. So it's the elevator, you can only control the one way. The springs automatically push it up. So this is what we use to climb. And we're got a very simple gearbox here. And that's what we're going to go over to design. So the question is, you need to know some data. So the first thing is that this is designed to lift a robot. That robot is 150 pounds. So that's a fair bit of weight. And what you need to do is you need to figure out, can you lift 150 pounds? And that's what we have a calculator for. So with the calculator, you have this linear mechanism and you can pick the motor. So I'm just going to pick for you. We're going to use the Neo motor. And the Neo motor is a nice, small, compact motor. And you can see it right there. And the nice thing with this particular motor is that it's got a fairly high amount of torque. And what that means is torque is how much weight can this lift. So basically, it can lift up to 2.6 Newton meters. So this is an amount of force, and if something is heavier, requiring more force than that, the motor will stall. So that's the maximum. And with Newton meters, you need to get into physics and everything. But this is why we're going to use a calculator. So we've got a calculator here, and basically you fill in the motor and it fills in the speed of the motor, the stall torque of the motor, what the current is, and the free current. And the biggest thing is that we need to keep our current under 40 amps. And then you can have how many motors in the gearbox. So if we had one motor, you can see this goes red because it's drawing more than 40 amps. So we know that this would not be enough to be able to lift 150 pounds. So if we had a smaller mass, then it could lift it. And unfortunately, our robot is going to weigh about 150 pounds, so it simply can't lift it. So we also have a few other pieces of information. The gearbox efficiency, we don't tend to change. That's usually with gearbox, there's friction. So 80% efficiency is usually a good benchmark for us. The number of motors, that can matter. The travel distance, this is how far our elevator is going to end up going. So you can see with their elevator, it extends about 33 inches in total. So we've put in 33 inches and we've put in our pulley diameter, and we could set that. The bigger the diameter, you can see it impacts it. It acts as a gear reducer depending on the size. But we had 0.775, and we've got different gears. So to go about gears, we usually get our gears from Vex Robotics. And the first thing is you always start with your motor pinion. So the motor pinion, this is the gear that goes on the motor. And you can see there's three types of motors that they list. The Neo is not one of them. And if you look at this um, with the Neo, you'll see it's a drop-in replacement for sim style motors. So we don't need to have a Neo, we can use a sim style motor. And you can see there's different size teeth with the different sim styles. So when you're looking at this teeth, there's the sim style, so 10 teeth and everything. If you go to the drawings, and we're just going to switch to, so these are falcons, 9 teeth, and here's our 10 teeth. So there's 10 teeth, and you can see there's something called the pitch diameter. So the pitch diameter is the distance um, of the circle where the teeth will engage with another circle. So that's really important. Now, normally, if we're dealing with 20 diametrical pitch, 20 dp, which is what these gears are, normally you can the number of teeth divided, and when we get to 12 teeth, you'll see that. So here's 12 teeth, and the pitch diameter is 0.6. 12 divided by 20, 0.6. 14 divided by 20, 0.7, etc. Now, when it gets really small, like 10 teeth, that kind of goes out the window. But anything bigger than 12 teeth or more, that we can use that as a formula, which is really useful. So we're going to start. I'm going to start you off. You're going to use a Neo motor with a 10 tooth pinion. Okay, so that's what we're going to start with. And when we're looking at this, we can see there's other gears. And so the 1/2-inch hex bore gears, there's our options. And you can see we've got a lot of different options here. And basically, any of these options. So let's just pick a 50 tooth gear and let's plug that into our formula. Now, we're going to use 2 motors because what we'll do is we'll do 2 arms. So we'll do 2 arms. And if we look at this, 34 amps, 10 to 50. So this should be able to do it. And it even tells you how fast it's going to take, just under a second to be able to move the full 33 inches. So this is pretty good. You can see we've got other options. And the biggest thing is that I would like to bring this down. I like about 25 amps because if I'm at 50 teeth, 34 amps, that's 40 amps is my breaker. If something goes wrong, I could easily go over the 40 amps. So let's say I've got my 150-pound robot, another robot lands on my robot, adding the weight up to 300 pounds. In that case, I spike and it's just not going to work. So if I'm going up to 68, it's still a little bit over, but it's much closer. So that's the goal, is to find an amount where you've got a fairly high safety factor, so that if something goes wrong, it should work out all right. So there we've got our amount. So if we look at our drawing, again, I mentioned 68, and the diametrical pitch, the pitch diameter, if I scroll down to 68, is 3.4. 68 divided by 20. Okay, so let's go over how to design our gearbox. So in this assembly, we've got everything, but we don't have the gearbox. Now we've set up our mounting holes. So that's good for us. We can use that. So what we can do is we can create a part in context. And we're just going to set the origin. And there's our part. Now, if we do a new, and what we want to do is basically we're going to have our pulley pull rope through here. And this is to have just a little bolt through here so that the rope is going to go around the a little spacer so that there's not much friction. It's not going to wear and cut on the edge of the metal. So that's the goal, is where we're going to put everything. And what we'll do is we'll create a sketch and we'll use this face as our guideline. Actually, I'm going to cancel that, because what I'll do is um, I'll start with some variables. So my first variable is simply a number, and it's diametrical pitch. And what we'll do is I like putting in my different gears. Gear 1 has 10 teeth. Gear 2 has 68 teeth. Now, gear 1, simply because I can't calculate it. So there's the 10.6. So gear 1, DP 0.6. Normally I calculate it, but for that particular gear, I can't. So I've got my teeth. Now I can create my sketch. I'm going to select that face. Now, what I'm doing is I'm going to create construction circles, letter Q, and letter C for circles. And what I'm going to do is I'm going to start with a circle right here, and I just hit escape. I'm going to go to my dimension tool, and this is going to be number sign gear 1 DP. So that's my motor. Okay. And I'm going to add another circle, and again, construction. And this time you see how I'm touching it, so it's tangent. The reason I'm hitting escape is because when I'm entering in variables, it's not as easy. So now I'm going to go, okay, gear 2 divided by my diametrical pitch. There's my 3.4 inches. Okay, so I have that. I have my motor. If I look at, this is my motor, I can see the body diameter is 60 millimeters. So what I'm going to do is I'm going to add another construction circle centered on that one. And the reason I'm doing that is I just want to make sure that I don't want this to be touching that wall at all. So that looks pretty good. You can see I'm going to use, and I'm doing the construction, I'm going to use this line. And the reason I'm using this line is I want a point right in the middle of that slot. And this point is going to be horizontal to it. So there we go. So I have my circle, and I'm going to make sure I don't want to be touching that at all. I'm just going to have a nice close thing so that circle is locked in place. And this I can move around wherever I want it, but you'll notice it's always touching that. Just for symmetry, I'm going to have it vertical to that. So there we are. So there's my sketch. So there's my gear geometry. And the beauty of this particular system is that if I decide I would rather use a slightly bigger gear, and obviously I'd do my calculations, I can modify it and everything is going to work because of how I've laid it out. So there's my position for my gears. So I'm going to create a new sketch. And so this is going to be my plate. So I'm going to use that face. And again, I'm going to use, this time I'm going to get these circles. And I'm going to select those points. And what I'm going to do is just going to use construction just so I've got it. Okay, so, oops, I missed that one right there. And I'll just do this line right there. Okay, so these are going to be my holes. Now I'm going to need a hole for this particular spot. So what I'm going to do is I'm going to create a circle. And this circle is going to be 1.125 times an offset. And I'll just do 0.01. So what this is, 1.125, and did that work all right? I don't think that worked. Number 1.125, or sorry, this is my offset 0.01. And you can see it adds that variable. So 1.125 is the diameter of a typical bearing that we use. So that's why I'm using that. And the offset, I always want to make sure to include an offset. So when I'm using the CNC machine, I cut it out and it's just slightly bigger so that the bearing fits. If it's the same size, it won't be. And by using it as a variable, I can mess around with it and change it. So my Neo motor as well, let's look at the drawing for it. And here's the drawing. And there is no drawing. Let's try this one. There we go. So you can see there's this little bit right here, 0.75 inches. And so I'll use that. And again, 0.75, I'm just going to add that offset. And you can see there's mounting holes. So the mounting holes are, there's 4 holes, and the holes are on a 2-inch diameter circle. Okay, so what I need to do is I need to figure out how I'm going to mount this. Now, obvious, the reason there's 4 holes is so that I can mess around. And I'm just going to use a line here. So 2 inches was the distance. Remember, whoops, I just want to circle. Remember, when we're dealing with number 10 screws, 1364 is the size. So you can see I'm putting circles on the ends, and I've got my equal sign. The letter E is equals, so those are equal in size. And what I'm going to do is I'm going to take the midpoint, and I'm going to click on that line, click on that point, and now these mounting holes are going to fit. Now, I can mess around with this, but I'm just going to use the letter H and horizontal. So those holes are not going to conflict with this gear. Everything looks good. So that's awesome. And what I'm going to do here is I'm just going to take a line here. And we'll just say 2 inches. And I'm just going to dimension that. I try to keep everything like 1/4 inch and stuff like that. So I'm going to just make a. So what I'll do is if I do a center point arc, I can go, okay, I'm going to go down here and I'll go somewhere around here. And it doesn't matter. What I'm going to do is I'm going to create a line connecting these two. And that line I'm going to set to be tangent. So by making it tangent, it will look really sharp. So that's good. I'm going to do a center point arc for this too. Boom, boom, boom. And what I can do is I can just dimension these. So just make very small, so it's just slightly bigger than the gear. But again, if I do a line and tangent the line to the curve, tangent the line to that curve, I can get a nice shape here. And again, tangent that line to that curve. And if I just set this line, everything's good. So I now have a sketch. Now there's lots of different ways we can do this. And I can extrude it. And just like that, I have a gearbox plate that can work. And using so I'm just going to fasten go back in. I can now use MKCAD. And what I can do is I can add my bearing. And I'm just going to go back to the previous. So you can see they've got fasteners in here. And you can see this is all organized. So that's 3/4 of an inch, which actually I think is too long. This should only be 0.22 inches long. And this is 0.125. So this should be 3/8. Somebody made it 3/4 of an inch, which is far too long. That would be an issue. So wrong thing. So basically, we've added a neo motor. On the neo motor, we've added a pinion, and we've added a gear. And you'll notice that we've got two separate plates here. Now, their technique in this particular one, and this works perfectly, just straight. It had been a while since I looked. I thought this was flush, but it's not. So the straight would work perfectly. And it's easier to make if it's straight. So that's probably a better solution. And you can see you've got the gear. If you hide the gear, you can see there's the bearing. So it's a 1/2 inch hex bearing. So there's 1.125. That's the outer diameter. So that's what we're talking about. And you can see with the bearing, we've created some custom parts so that way everything fits perfectly. And you've got the shaft. So you'll notice with the shaft, we've got this external ring, and that ring is what holds it in place so that it doesn't just slide out. and we're missing that. There's a type of ring that should be on here, and there should be a keyway, which is just a little piece of steel, 2 millimeters by 2 millimeters, so that that locks the pinion with the shaft so that it goes around, and then this retaining clip goes on top. But you've got the basic premise. The biggest thing is making sure that your holes line up, and you can see when the gears line up. Now we would need to rotate them, but these teeth, if this was rotated, the teeth would actually fall right inside, allowing it to make contact and rotate. So that's how you do it.